Okay, so just before we look at nth terms of quadratic sequences, just a very quick recap on nth terms of linear sequences. So a linear sequence will be something like, well, when numbers are going up in equal steps. Let's say we have a 2, and let's say it's going up in 4s. So we'll have a 6, we'll have a 10, we'll have a 14, we'll have an 18, and so on. So this is a linear sequence because it's going up in equal steps. So when we look at these differences, okay, we can see that it's going up in 4s. Okay. Now, if something's going up in 4s, we compare it to something else that we know goes up in 4s, like the 4 times table. So if I compare these numbers to the 4 times table, which is 4, 8, 12, 16 and 20, I'm hoping that you can see that this 4 times table, if I take 2 off of each of these, I get back to the sequence here. Okay, so if we think about the 4 times table as the nth term of this is just 4n, where n is the term number, so 4 times 1 gives me 4, 4 times 2 gives me 8, 4 times 3 gives me 12, and so on. All I have to do to get the top sequence is I have to do the 4 times table, which gives me these numbers, and then I have to take away 2. So I call this number the adjustment. So the adjustment here is take away 2 from the 4 times table to give the sequence that we're looking for. Okay, so that is how we get the nth term here, the formula for the nth term when numbers are going up in equal steps. If they're going down in equal steps, well, let's have a look at an example. Let's say we have 50, and we'll say it's going down in 3s. So we got 47, 44, 41, 38, and so on. So we can see again this is a linear sequence because the gaps are the same. The first difference in each case is to take away 3. Yeah, so the gaps are minus 3. So the way we actually work out the nth term for this is we think about it slightly differently to the example above. If it's going down in 3s, it means that basically the nth term is going to be of the form of some number take away some multiples of 3, so the 3n. Okay, so we've got to know that the main thing here is to work out what this missing number, what number do we start with here, so that when we take off multiples of 3, because that's what the differences are, we're taking 3 off each time. So what number do we have to start with? Well, if we look at the first term here of 50, that has already had a 3 taken off of it, because it's going to be a number here, take away 3 times 1. So we'll be taking 3 off. So I'm hoping you can see that in order to get that first term, I would have had to start with 53. Because 53 take away 1 lot of 3 gives me 50. Yeah? And then the next term would be 53 take away 2 lots of 3, which would be 47, and so on. So here is my nth term. It is literally just 53 take away 3n. Okay, so now let's look at a quadratic sequence. First of all, how do we spot it's a quadratic sequence? Well, let's look at an example to be able to explain that. So let's say we have a 6, 11, 18, 27, and 38. I think straight away, just intuitively, you can see that the differences here are not the same. So we know it's not a linear sequence, it's not going up in equal steps. But we still need to look at what the steps are. And hopefully you can see the first one there is 5. Then this one is going up 7. Then this one is going up 9. And then the next gap is 11. Okay, so these are called the first differences. Okay, now if they're the same, then obviously it's a linear sequence, but these are not the same. So now we need to look at the second differences, in other words the differences between the differences. So let's look at that. So from 5 to 7 we're going up 2, from 7 to 9 we're going up 2, from 9 to 11 we're going up 2. These are called the second differences. Now if the second differences are equal, as they are in this case, that tells us that it's going to be a quadratic sequence, a quadratic nth term. So we know there's going to be a squared term in there. So basically quadratic sequences are going to be of the form, the nth term is going to be of the form n squared plus bn plus c. Now the bn plus c is linear. And we'll come back to that later on. The first step in finding a quadratic nth term is to determine what the a is here. In other words, how many lots of n squareds have I got? And the key thing here is that a, the value of a here, will always be half of these second differences. Okay, so because the second difference here is 2, a will be 1 in this case. If the second differences were 4, we'd start with a 2n squared. If the second differences were 6, we'd start with a 3n squared, and so on. So here we're going to start with 1n squared. Okay, so we know that n squared would give us the sequence 1, 4, 9, 16, 25, because they're the square numbers. So that is what n squared would give us. It would give us this sequence here. Obviously 1 times 1, 2 times 2, 3 times 3, and so on. So what I want to find out is that if my n squared part of my formula, part of my nth term, gives me 1, 4, 9, 16, 25, then what am I left with? Because obviously I started off with 6, 11, 18, 27 and 38. So what I can do is I can subtract. So if I take away and see then what I'm left with. So if I do 6 take away 1, I get 5. If I do 11 take away 4, I get 7. If I do 18 take away 9, I get 9. If I do 27 take away 16, I get 11, and if I do 38 take away 25, I get 13. So my n squared part of my formula will give me these numbers, and my linear part, so this part here, the bn plus c, has to be this part, so that when I add them together, the 1 plus 5 will give me the 6, the 7 plus 4 will give me the 11, the 9 plus 9 will give me 18, and so on. So all I've got to do now is find the nth term of this linear sequence. Well, I can see it's going up in 2's, okay, so I know it's 2n, got a b to do with the 2 times table, and if you compare it with your 2 times table, 2, 4, 6, 8, 10 and so on, I'm hoping you can see that we have to add 3 to the 2 times table to get the linear sequence we're looking at. So it's plus 3. So if I now combine these together, my quadratic nth term overall is going to be the n squared here, okay, so it's n squared, and then the linear bit here, so it's plus 2n plus 3. And that nth term would generate the sequence that we started with up there. So let's look at one more example. This time we'll start with 3, 12, 25, 42 and 63. Okay, we work out the first differences. So if we work out the first differences here, we're going to get 9, 13, 17 and 21. They're obviously different, so we have to work out the second differences. So if I work out the second differences, hopefully you can see all the second differences are 4. So because the second differences are 4, I halve 4, and that tells me how many n squareds I've got in my nth term. So half of 4 is 2, so I know I'm going to have 2n squared as part of my formula. So let's write down what 2n squared is. Well, 2n squared is just double all the square numbers. So instead of 1, 4, 9, I'm going to have 1 times 2, which is 2, 4 times 2, which is 8, 9 times 2, which is 18, 16 times 2, which is 32, and 25 times 2, which is 50. So this 2n squared will give me these numbers here. So now I need to work out what that leaves me with. So if I started with 3 and I take away the 2, that leaves me with 1. The second term, if I started with 12 and the 2n squared gives me 8, then that leaves me with 4. I started with 25 and this gives me 18, so that leaves me with 7. And if I carry on, 42 take away 32 is 10, and 63 take away 50 is 13. This is now a linear sequence, so I can work out the linear part, and we look at the gaps. So the gaps are 3 each time. So because the gaps are 3, I know it's to do with the 3 times table, so we get 3n. And if I compare it to the 3 times tables, so the 3 times table is obviously 3, 6, 9, and so on. And can you see that to get from the 3 times table to the numbers that I want in my sequence, I have to subtract 2. So my nth term is 3n minus 2 there. So I now combine my quadratic and linear bits together to get my overall quadratic nth term, and my overall answer is therefore 2n squared plus 3n minus 2. Hope that makes sense.